All right. Hello, everyone. It's my genuine privilege and pleasure to introduce our Colloquium series speaker. In this series, that's a jointly organized between the departmental Colloquium series and the IEEE SSCS and CAS societies. Our speaker today is Dr. Keith Bowman. He is a principal engineer and manager in the processor research division at Qualcomm. And his mandate there involves not only exploring and inventing new technologies for current and future generations of microprocessors, but actually translating them all the way into production silicon, which tends to be a rarity. So we're really glad to have him come and provide us with this presentation. He's published a large number of papers. He has over 80 publications, a lot of them notable, which I read when I was a grad student. But more recently, he's very well known for designing, testing, and essentially putting into production Qualcomm's first circuit technology that allows them to withstand voltage droops and thus avoid the very debilitating efficiency impact that these supply droops have. And I think we'll get a chance to listen to some of that work as well. Prior to Qualcomm research, Dr. Bowman's held positions at Intel, where he was from 2001 to 2012. He was contributing in both the technology and CAD divisions, as well as Intel Circuit Research Labs. So yes, without any further ado, I'd like you to just welcome Dr. Bowman, and thank you.
Thank you very much, Professor Satya. I want to thank you as well as Professor Rodell for inviting me to be here, and also want to thank each of you for attending this seminar. And before I get started with the presentation, I first want to highlight the sponsorship is from both the IEEE Solid State Circuit Society, the SSCS, as well as the Circuits and Systems Society, CAS. And these are really important societies. I think as each of you, when I think back when I was in graduate school, I was a part of these societies, and these were really instrumental in learning some of the state-of-the-art research and developments that were happening in the field. And what's really important is when you get that wonderful diploma and you graduate from this university, you're going to have a continual learning experience, a lifetime of learning. And I find the IEEE to be instrumental to that process. And so I've remained a member throughout my career, and I would encourage you, if you haven't signed up, to consider doing that and attend an IEEE-sponsored conference. There's many educational opportunities, networking opportunities. Actually, Professor Satya and I, we met each other through a conference as an example. And there's tremendous leadership opportunities, tools for career growth, as well as recognition. And as far as some of the Solid State Circuit Society educational material, this consists of distinguished lectures like today. There's webinars, there's like 12 a year, and these are typically from well-known speakers on topics that would be relevant to the fields across the Solid State Circuit Society. There's a conference educational series, as well as a Solid State Circuit Society educational series. These are terrific because these are really opportunities of learning some of the latest transitions that are happening in our field. There's design contests, book series, and one of the things I'd really want to highlight is there is an archive of tutorials at various conferences, such as the International Solid State Circuits Conference, ISSCC, or the Symposium on Villa-Sized Circuits, or the Custom Integrated Circuits Conference. And you get access to this by being part of these societies. And some of the material is you can actually get through YouTube. So I strongly encourage, if you have an opportunity, if you haven't yet, to look into joining these societies. And even while you're a student here and when you graduate, still consider to be part of the IEEE. Okay, so now I'm going to jump into today's presentation. And today we're going to talk about adaptive and resilient circuits specifically for processors. So variability in device, circuit, system parameters is one of the primary challenges in the semiconductor industry today, in that it degrades processor performance, energy efficiency, and yield. And if you do a broad classification of the variability, it falls into three primary categories. These categories consist of uncertainties in our simulation tools because we're using static timing tools to estimate dynamic events, so there's uncertainty there, there's going to be variation. There's also variation that results from the manufacturing process. There's going to be variations in transistor dimensions and interconnect dimensions from die to die, as well as across a die. But for a given die, these variations, once you've manufactured the chip, they're fixed, they're static. And then there are variations that occur during the lifetime of a part, during the lifetime of the operation. And we refer to this as a dynamic parameter variation. So if you look at like a processor company, such as I work for Qualcomm, used to work at Intel or AMD, any of these processor companies, we test our processors, and when we do a testing, we typically are going to do one of two types. We're either going to have the voltage fixed, and we're going to sweep frequency, and we're going to see what's the maximum clock frequency in which that processor will operate. And so because of these static variations, you might get a distribution of Fmax across the parts. Similarly, another type of test, so that's called a maximum clock frequency test, or Fmax. And then there is also sometimes we will fix frequency and we will lower voltage until the part fails. That's called a minimum voltage test, or we call that Vmin, a Vmin test. And so again, due to these static variations, there can be a distribution of parts from die to die based on these static variations. But the key point is because we perform these Fmax and Vmin tests, we're adapting to these static parameter variations. So the variations due to either the tool uncertainties or the manufacturing process, the worst case variations is not going to affect the entire distribution of parts as a whole, because we're adapting either the voltage or frequency to account for that. But in contrast, the dynamic sources of variation, these are variations that are based off of estimates of our product specs, and these are, I'm going to talk more about this, but we have to actually insert guard bands either in the frequency or voltage. We have to either operate at a lower frequency than ideal, like we'd rather operate at, or we have to operate at a higher voltage than necessary. And the key point is these variations affect the entire distribution of parts. They have an enormous effect because of that impact on the entire distribution. So the focus of the seminar today is going to be specifically on these dynamic variation sources and how we can use adaptive and resilient circuits to mitigate these dynamic variations to enhance processor performance, energy efficiency, and yield. And the outline I'm going to go through today is I'm first going to talk about the primary sources of dynamic variability. Then I'm going to talk about the impact of these dynamic variations specifically on logic design. And then I'm going to go into adaptive and resilient circuits. I'm going to break this up into 4 categories. First, I'm going to talk about what I refer to as a traditional adaptive design that specifically focuses on slow changing variations. Then I'll talk about resilient designs, which can mitigate both fast and slow changing variations. And then I'll describe adaptive designs specifically targeting fast changing variations. And finally, I'll talk about some future adaptive designs and then summarize. So high frequency supply voltage Droop is one of the primary variation, dynamic variation sources. This is one of the largest impacts that we have on our process today. And this results from an abrupt change in the processor activity. It induces a large current change, a large current transient in the power delivery network. So we refer to this current change a DI over a short amount of time, DT. So this DI dt multiplied by the inductance creates this Droop effect. And what we've seen from measured data is that primarily this Droop, the inductance, is primarily in the package. And so it's seen as a global effect across like a CPU area. And it occurs very quickly. So from nominal to the minimum value in voltage can be in the range of like 2 nanoseconds. It can happen very quickly. Another important point to note about these high frequency supply voltage Droops is although it significantly degrades the performance of the processor during this time, it occurs very infrequent for typical workloads. So this is something that aims itself or allows itself to be mitigated by adaptive and resilient circuits because it occurs infrequently. Temperature variations change due to processor activity or the ambient conditions, but the time scale is much larger. The time scale is going to be in the range of hundreds of microseconds to a millisecond. So it's a much longer time scale in which is variation. So I would kind of refer to this as a slower changing variation. And then there is transistor aging, which is referred to as bias temperature instability, BTI. BTI, and the BTI effect, depending on the workload, can actually occur over days, or hours, days, weeks, months. It can take a long time for this effect to occur. So this is a very slow changing variation. Again, it depends on the workload. And here in this figure, on the left y-axis, this is plotting this drive current degradation versus the peak GM. And I want to show this data. This is data from Intel because it kind of highlights some of the key physical mechanisms that's creating this aging effect. And here we see in this plot is we have the PMOS negative bias temperature stability, NBTI. That is the solid circles. And we have the NMOS positive bias temperature stability, PBTI, and that is the opaque circles. And this is plotted versus the peak GM. And what we can see is that the reason that they did this is because the peak GM is primarily dependent or correlated to the mobility. However, it's mostly independent of threshold voltage. And so you can see, because there's such a strong correlation between the drive current degradation and the peak GM, this indicates that primarily the aging effect is the interface damage that occurs on the dielectric to the silicon, that interface, and that's degrading mobility. And in the case of the NMOS, we can see is that there's really no effect on the peak GM as we have the drive current degradation. So this indicates that primarily this is due to traps that are occurring in the dielectric, and this is what's shifting the threshold voltage. So both the PMOS NBTI or NMOS PBTI degrade the processor performance as shown in this graph on the right, and this is showing the path delay change across a number of paths across an amount of stress time. So this is like operating a high voltage and high temperature condition, and we can see that the path delay degrades over time as shown in this figure. There's also variations due to the workloads, and here is a plot from a non-tech and evaluating the system power versus time. And what I want to really highlight here is that there's tremendous amount of variability even within a workload. So for example, this video editing workload, there's tremendous variability as well as from workload to workload. And so this is important because a lot of the processor parts, especially I work at Qualcomm and we have the SoCs that go into smartphones, and we hear a lot about the power condition. And so if you need to maintain a target power envelope, understanding these workload variations and adapting accordingly is a significant opportunity as well as a challenge. Okay, so now what I'm going to do is I'm going to go into the impact of these variations on the design. So to start, I'm going to look at a very simple path. So I have a driving flip-flop, some logic in between, and a receiving flip-flop. And if we look under the worst case dynamic variation events, which is shown in this timing illustration with the red curve, the data, the input to the flip-flop must arrive when it transitions, must arrive a setup time delay prior to the rising clock edge in order to satisfy the timing margin. So timing margin is the clock period minus the data path delay, and we have to account for that setup time. So under the worst case variations, we have to guarantee that we satisfy this timing constraint. So what that means is under nominal operating conditions, if there's no droop, the temperature isn't high, and so forth, or the temperature is not degrading. By the way, the temperature effect can be worse at higher or low depending on other conditions. I won't get into detail now. But the point is that under nominal conditions, the same transition, the same path delay is going to occur much earlier in time as shown in this blue curve. And so this gray region corresponds to the timing guard band that needs to be built in to ensure correct operation in a conventional processor design. And the way this is achieved is, as I mentioned earlier about the Fmax test or the Vmin test, is either you're going to operate at a lower frequency than under nominal conditions, and that means you're building in a larger cycle time, and so that's hurting performance, or you're going to operate for a target frequency, you're going to operate a higher voltage to account for these dynamic variations. So you're either building your guard band in frequency or voltage. And if you do it in voltage, now you're really hurting the energy efficiency, the power, because now you're spending a lot of power to ensure you have correct operation for these infrequent variations. But the problem is that you don't know when they're going to occur, and you have to ensure correct operation. So it significantly degrades the performance or energy efficiency of the processor by providing this additional timing margin. And this is what processor companies have done for many, many years in trying to address these dynamic variations. And now if we stack these variations into a frequency guard band, so we look at this and here is a plot of like a frequency guard band, and I'm looking at two different modes of operation because processors today operate at a high performance mode, so high voltage, high frequency, and a low power mode, which would be a lower voltage and a lower frequency. And so at the high performance mode or the low power mode, there's going to be, as I mentioned earlier, so there's temperature, aging, the voltage droop. There's also variability. We have to account for the voltage regulator because on a board, the regulator is going to have some specs to it, and we have to account for that variability. And there's also a variability that has to be accounted for the system to tester miscorrelation. Because when you look in a product environment, when you're in high volume testing, you're going to be testing the part very quickly on a tester. And so the environment is completely different than a normal system environment where you're actually running actual workloads. In a tester environment, it's going to be tests that are specifically activating what is believed to be the critical paths. And so for that reason, there is just going to be variability because they're completely two different environments. But the goal of the tester is to do this very quickly so you can get the part, because testing cost is a significant component of overall cost in designing, manufacturing, and testing of a processor. So you have all these guard bands that are built up, and if we were to account for these at the high performance mode, this is approximately about 30% of the entire cycle time today if we looked at these variations. And as you go down to a lower voltage, as you scale your voltage, then the delay sensitivity to these variations are going to amplify. They're going to be much more sensitive, so the dynamic delay variation is going to be greater. And at low power mode, this can consume approximately 50% of the cycle time in a modern processor. So these variations significantly degrade performance, energy efficiency, and the reason it affects your yield is because you're going to have specs on a part that has to either satisfy a power or performance target, and if you have those guard bands that are either degrading your performance or degrading your power, then you cannot sell that part, and that's a big point about how it affects the yield. Furthermore, as we look forward to Internet of Things devices, IoT, these processors, the requirements are going to amplify the effects of dynamic variations. And this is when we consider when IoT, you're going to be looking at much lower costs packaging, and that's going to result in worse supply voltage droops. There's also energy harvesters, which can vary significantly in the voltage that's received. That's going to have a significant effect. There's a much wider range of temperature conditions when you actually think about autonomous vehicles and the conditions a car can be located as compared to like a smartphone or your laptop or desktop. And there's also the lifetime requirements are much, much longer, especially when we start talking about autonomous vehicles and so forth. So we expect all these kinds of effects are just going to make the impact of these dynamic variations much worse. Now, as I go through this presentation today, I'm going to talk about adaptive designs and resilient designs. And when I talk about these, I have a specific definition that I'm referring to. And I'm using the Merriam-Webster to provide some guidance here. So when I talk about an adaptive design, I'm specifically talking about a design that's going to detect a parameter change, and then it's going to adjust the operating condition, for example, changing voltage or frequency, to avoid any errors from occurring, either timing errors. When I refer to a resilient design, here I'm leaning on the recovery aspect of the definition. And here, resilient design is actually going to allow a dynamic variation to have an error within the processor, but it's going to detect the error and then it's going to correct it such that it maintains overall system functionality. So that's how I'm distinguishing between adaptive and resilient designs in this presentation. And both of these designs mitigate guard bands to improve the performance, energy efficiency, and yield. It's also important to note that when we look at today's processors, we care about a wide range, a dynamic range of operation. And here's a plot of voltage versus frequency. And today we operate at a high voltage, like a turbo mode for voltage, which is typically either going to be limited by the reliability or the power constraints, but that's our highest performance mode in which we can operate. And then we also going to operate at different conditions where we're going to scale voltage and frequency, and we even go down to the lowest operating voltage at which we can operate. And here we can have like the lowest voltage, like here is referred to a Vmin versus the frequency of the min. And typically, the low voltage operation is limited by the memory circuit failures. So that's one of the keys that's limiting. And as we look at adaptive and resilient circuits, the idea is that we want to expand this operating range. At turbo, for example, we want to be able to operate at a much higher frequency while maintaining the same voltage. And at the low end, we want to be able to operate at a much lower voltage for the same frequency. So adaptive resilient designs provide an opportunity for expanding this range of operation. Furthermore, there's a wide range of platforms that processor companies are building towards today. And so if you look at a company like, again, Qualcomm or Intel or AMD, NVIDIA, there's a wide range of platforms that the company is designing to. But instead of having a specific design for each of these platforms, we would like to ideally just have a couple of designs serve across the entire spectrum of the different types of devices, like all the way from server, tablet, phone, as well as like IoT devices. And these different platforms have different power, performance, different types of cores, thermal, ambient conditions, as well as reliability, availability, and serviceability. That's RAS conditions across the different spectrum. And so we'd like to just have a couple designs to support these different platforms, and this is where we want to look at having adaptive and resilient circuits to satisfy these different constraints. So now I'm going to jump into adaptive resilient circuits, and I'm going to first start specifically with adaptive designs targeting slow changing variations such as like temperature. So here is a traditional adaptive design, very simple illustration, where we have a number of sensors, such as like a thermal sensor, a voltage sensor, an aging sensor. And this is actually put into the die, and it's going to detect a parameter change, such as like the temperature, the voltage, or the aging. And then once it detects the variation, it's then going to interface with a dynamic voltage frequency control to either adjust the voltage, maybe through like a voltage regulated module, a VRM, or through a clock generator to change the frequency to avoid any timing violations. So one of the key attributes of these traditional approaches is that the overhead is very low. It's a very small overhead. It's not intrusive to the design, and this is one of the big attributes. So as an example of a traditional adaptive design, here is a measurement of a test chip that's demonstrating adapting to temperature variations. And so on this the top y-axis is temperature, the bottom left y-axis is frequency of the part, and the right y-axis is the body bias, and the x-axis is time. So initially when we start, you can see that the temperature is about 60 degrees Celsius, or just below 60 degrees Celsius, and the frequency is at a higher value, it's at the highest frequency value. The body bias is in a forward body bias condition, and the main point to know about body bias is that when you forward body bias a transistor, you're making it faster at the cost of leakage. You have a lot more leakage that's happening due to that. So in this case, when the temperature is below 60, that is the optimal scenario. But once the temperature exceeds 60 degrees Celsius, then it's going to detect that change through a thermal monitor. And the first thing it's going to do is going to lower the frequency, the operating frequency of the design, and then it's going to take away the body bias condition. And the reason is because once we go to higher temperature, the leakage current is going to exponentially increase at the higher temperature. So this allows the design to optimize the performance and power across this thermal profile. And then eventually, when this temperature goes back down due to the workload changes and it goes below 60 degrees Celsius, then the first thing it's going to do is going to apply the forward body bias to make the transistor faster at higher leakage. And then with that, then they're able to now increase the clock frequency to the higher value as shown here. So the key is that this design adapts the frequency, the clock frequency, as well as the body bias to ensure correct operation and the optimized power, especially the leakage, at the higher temperatures. Now there's also work that's looked at doing this traditional design approach for mitigating fast-changing variations, such as a high-frequency supply voltage droop. And there was work that was done at Intel, and this is the most recent work that was done at AMD. And here is showing the idea is that the supply voltage is going to droop due to that change in current, that DIDT effect I described earlier. And the idea is to detect the droop, and then you're going to adaptively change the frequency. You're going to reduce the frequency such that the timing margin is maintained. You're not degrading the timing margin. So the key idea is you're going to detect the droop and then adapt by stretching the clock period. I want to highlight this design is an elegant design because this design, so you have a phase lock loop as a PLL, and then you have a droop detector circuit that interfaces with a digital, a DLL, a delay locked loop, excuse me, and a phase picker. And what's really elegant about this design is that they change the frequency as needed based on the droop that's detected, and they allow a resolution of about 5% of changing the frequency. So there's a really nice feature in this design. The challenge of this design is highlighted in this figure, and here it's showing a droop that's occurring and how the clock frequency and how they're going about changing it. So here's a plot of voltage versus time, and this is what is showing like the droop looks like. So once the voltage degrades beyond a certain value, a threshold, they're going to detect the droop. That's going to take some time. And then it's going to take time to synchronize that communication, that sensor that detected the droop, to the clocking circuit. That typically takes about 2 cycles to synchronize that in order to change the frequency. And so what happens here is that in order to recover a portion of the clock frequency loss or the timing margin, the processor frequency has to operate much, much faster than the resonant droop frequency. That's the frequency of the droop itself. And so in this example, the processor is operating at 3.4 gigahertz, so they are able to mitigate a small portion of the droop when this occurs. But one of the key takeaways from this talk, when we look at these traditional adaptive designs, if we would actually operate it at a lower frequency, say 2.5 gigahertz, well, by the time you detect a droop, and then you adaptively change the frequency, well, the timing margin degradation has already occurred. So the key problem with the traditional adaptive designs is that response time limits the benefits. That's a key issue with this, because if we have a very fast changing variation, such as a high frequency droop, that's what's going to limit or prevent our designs from working. And so this is a key limiter for these traditional adaptive approaches. So now I'm going to transition to a resilient design approach, which is able to relax this response time constraint. So here in the resilient design, the idea is going to operate the voltage and frequency based on nominal operating conditions, and then the resilient design is going to detect and correct the timing error due to these infrequent dynamic variations, and the benefits in throughput and energy efficiency are going to result directly from mitigating these dynamic variation guard bands. And today when I talk about the error detection circuit, so I'm going to talk about error detection and error recovery. There are 2 types of error detection circuits. So the error detection is the error detection sequential, an EDS, and the second type is a tunable replica circuit, a TRC. So if you go back to that simple flip path that I was showing with the driving flip-flop, the logic, and the receiving flip-flop, I'm now replacing that receiving flip-flop with an error detection sequential, an EDS. And this EDS circuit has a latch and a data path, as shown here, and it has a shadow flip-flop. When the data arrives, it's going to sample the input twice. The input is going to be sampled first by the flip-flop on the rising clock edge, and it's going to be sampled by the falling clock edge by the latch, and then the outputs of the latch and the flip-flop are going to be compared to an exclusive OR gate to generate an error signal. So let's look at a timing diagram. So here, initially, the data is arriving on time. So what happens is when the data arrives, because it arrives a setup time delay prior to the rising clock edge, the flip-flop is going to sample a low value, the latch is going to sample a low value, and so it's a 0 and a 0, an exclusive OR to 0, 0, the error signal is a 0, so there is no error occurs. But here, in the next cycle, we have a dynamic variation, such as like a supply voltage droop occurs, and now the transition on D is going to arrive late. It's going to arrive after this rising clock edge. So for that, what's going to happen is that the flip-flop is going to sample a 0 value. So that's a wrong value. And then the latch will then see the output, the transition, which will become high. And so the latch is going to have a 1. The flip-flop is going to have, on the output, the flip-flop is going to have a 0. And so when you exclusive OR 1 and a 0, that generates a high error signal. And this high error signal is then going to be combined with other EDS error signals within a pipe stage, and ultimately it's going to be flopped to generate a single pipeline error signal. And that single pipeline error signal will be used to invalidate this erroneous data and then be able to replay that error instruction. I'll talk about that a little bit later. Some key attributes I want to talk about this is, first, note that we have a latch in the data path, and the flip-flop it's a shadow flip-flop. And there's prior designs that had a flip-flop in a data path, but the problem with that is that if the data arrives close to the setup time, then the flip-flop can become metastable. And if it's affecting the data path, then that can actually result in a potential undetected error. It's a very high probability because of the metastability that can occur. So by moving the flip-flop from the data path to this shadow path, it only affects the error signal. And the error signal, as it turns out, behaves very similar to a synchronizer, and that's typically how you address metastability issues. So this significantly improves the mean time between failures due to metastability by putting that flip-flop only affecting the error path. So the latch, if you were to look at this latch, so this latch, you might look at this and say, well, hey, the data is correct in the data path, right? We captured the correct value. Why are you going to flag this as an error? Why don't you just move on and just say, hey, everything is good? And the reason we do that is because when the dynamic delay variation occurs, if we have back-to-back cycles of critical paths that are delayed, we could exceed the subsequent pipeline stage's error detection window. And so for that reason, we have to flag this as an error in order to recover from this late timing transition. Now, if you knew, like from your static timing tools, that you had sufficient timing margin in the subsequent pipeline stage, then you wouldn't need an EDS. You could just simply put a latch here, and you could use what's called traditional time borrowing. You could borrow time from that subsequent stage. But most of the processors today, the pipeline stages are balanced, and so I think the opportunities are rare to do that. And so for the EDS, even though the latch has a correct value, we must flag this as a potential error, and we need to recover from this scenario. The other point I want to make is that when we look at this EDS, one of the keys is that we're measuring when the data transitions from when the clock transitions high to when the clock transitions low, right? So that is what we refer to as this error detection window. So because of this, if you look at your max delay path, your slowest path in a design, typically we think of, like in a conventional processor, that max delay path must be less than or equal to the cycle time. Well, now it's going to be relaxed to less than or equal to cycle time plus this error detection window. So this error detection window is a potential benefit that you can have in the performance. And of course, that provides this classic trade-off for these EDS circuits where you have the min delay versus the max delay. So as I mentioned earlier, for the max delay, it relaxes the timing constraint because now you have the cycle time plus the error detection window. But it directly penalizes the min delay path because a typical min delay path your min delay must be greater than or equal to the clock skew from the driving flip-flop to the receiving flip-flop. Now it has to be greater than a clock skew plus this error detection window. And that results in two key choices that have to be made. So one is that you have to often insert min delay buffers to increase that min delay, and that adds power. And second of all, you have to have a clock duty cycle control to maintain a constant high phase delay. Because if you were to lower your frequency, if that high phase delay increased, then you'd be guaranteed to get a min delay failure. So you always have to have a clock duty cycle control for these EDS circuits. And this would have to be calibrated on a per part basis. Now there's a lot of work, there's a lot of research on these error detection sequentials in the literature. And there's a number of pros and cons for different types. And in the broad brush, I'm going to argue that there's basically two basic types. One is the one I just described, this double sampling error detection sequential. Another is a transition detector. And so if we look at the transition detector that's shown on the right, the latch is still remaining in the data path, but now instead of using the master-slave flip-flop, we use a dynamic gate to determine if the error has transition. So when the clock is low, when this value is low, it's going to pre-charge this intermediate node. And of course, the error would then be low, because this will be high and this will be low. And then once clock goes high, now this is what's called a valuation state for a dynamic gate. If the data then transition while clock is high, so remember within that error detection window, then what's going to happen, it's going to have the value is going to immediately go through an exclusive OR, and it's going to exclusive OR the current value with an old value, and then eventually it's going to go through a delayed version. And that generates a pulse on the output of this exclusive OR, and that's what's going to evaluate this dynamic logic gate. And so when this transition occurs and this value is high while the clock is high, it's going to discharge this node, and then the error signal goes high. So the key is that the nice attribute of this design is that it reduces the clocking power that's required for doing an EDS circuit. And that's a significant benefit because the master-slave flip-flop has much higher clocking power. However, it does not scale as well at low voltage. And that's really the big problem with these transition detector designs. And that's why the double sampling approach is one that tends to work a lot better. So now I'm going to transition from the error detection sequential to a different type of detection mechanism, and that's called a tunable replica circuit. And the tunable replica circuit consists of a toggle flip-flop, and it's driving a tunable delay, and ultimately it's going to, at the end of this tunable delay, it's going to drive another EDS circuit. And the key point is that the TRC is going to monitor the critical paths, but it's much less intrusive because we're not actually affecting the actual critical paths on the chip. So that allows it to be a much easier design. I don't have to worry about min delay constraints that I talked about earlier with the EDS circuits. And then what's going to happen is we're going to place these TRCs, as shown below, physically in the same proximity as the different pipeline stages as shown in this example. And then what's going to happen is that we're going to calibrate each TRC to track the critical paths per pipeline stage. And then when a dynamic variation occurs, the TRC is going to initiate the failure. So the key is that you have to guarantee that if any actual critical path failed, the TRC would also fail or fail before. So therefore, you have to provide a little bit of guardband. You have to make it a little bit slower, but you're able to reduce the majority of the dynamic variation events. So the TRC must always fail if the critical path fails. Now I'm going to move on to error recovery. And here is a range of different error recovery mechanisms. There's local error recovery where you can inject the correct value into the pipeline, and then you would stall for a cycle, and then you're able to continue operation. And there's an instruction replay where you just completely invalidate the instructions and re-execute. And there's also a software checkpoint and rollback where you periodically save the system state in memory and you roll back to the last saved state. And so as you go across from local recovery to the checkpoint and rollback, the benefits of local recovery is that the overhead from recovering from a dynamic variation is much less. It's much less of an effect. However, the circuit complexity is much greater. So from the point of view of the checkpoint and rollback, that is something that is easier to implement, but you're not able to reduce as much of those dynamic variation guard bands because the overhead for doing the recovery. So here's an example of the instruction replay where it's been replayed at half the frequency. So in this example, the pipeline errors, so when a dynamic variation event occurs, either the EDS can detect the droop and then ultimately propagate, it's going to OR with other EDS error signals to generate the pipeline error signal, or just simply the TRC by itself to generate that pipeline error signal. And then that pipeline error signal is going to propagate to the write-back stage to invalidate the erroneous instructions. Then the error signal is going to drive an error control unit to replay the error instruction. And this is very similar to a branch misprediction, like in a traditional processor. But when we replay this error instruction, what we're going to do is we're going to change the clock frequency because we have a clock divider, and we can switch this mux to operate at the half frequency. And when we're using the error detection sequential circuits, remember we have to use that clock duty cycle control because we have to maintain the high phase delay. We can't go beyond that high phase delay for min delay protection. And this allows us to operate when we do the replay of the instruction. We're operating at half frequency, and then after the instruction has been correctly executed, we then transition back to the target frequency. So here's some measured data that shows the benefits of the resilient design relative to a conventional design. And on this plot, on the top y-axis, we're showing throughput normalized to a conventional design. The bottom left y-axis is the number of recovery cycles from when a dynamic event, a timing failure, is detected and corrected. And then the x-axis is clock frequency. So if we take the processor, and it's a test chip, if we take a processor and we run at the highest operating frequency, we can run right at the edge, the right edge of this gray region, which is about 1.45 gigahertz, I believe. And if we induce a supply voltage droop of 10% during the operation, then the performance of the same processor is going to degrade to about 1.26 gigahertz, and that's going to correspond to this normalized throughput of 1 for the conventional design. So if you look at this gray region corresponds to the F-clock guard band that would be required for a conventional processor to ensure correct operation within the presence of a 10% supply voltage droop. Now, we look at the EDS design. We're now looking at throughput versus a clock frequency, and throughput is the product of instructions per cycle, IPC, and clock frequency. So as we increase clock frequency, we're going to get a linear improvement in throughput without any errors present. Now, once we go into this guard band region, now what's happening is that as we increase the clock frequency, the supply voltage droop is going to result in timing margin violations, which are going to be detected and corrected. And because we're replaying that errant instruction, it's going to degrade the IPC. The IPC is going to degrade. So when we look at the bottom plot of the recovery cycles, we can see this on a log scale. So initially, at least throughout this guard band region, it has a very small effect on the overall IPC from doing that recovery. In other words, it doesn't happen very often, okay? And then for this particular application, as the frequency goes beyond the F-clock guard band region, what this is actually illustrating is that it's actually under nominal conditions, it's running faster than the slowest critical paths, but because this application, it's not activating those critical paths frequently. So you can actually get a small benefit. Really, for this application, it's like 1 or 2%, where you're actually going faster, and then when you do exercise those paths, you're going to detect that, and then you're going to replay the instruction at half frequency. When you reach a maximum point, if you continue to increase frequency, the degradation in IPC outweighs further gains of increasing frequency, and that's why the throughput degrades. So we can see once we go through this F-clock guard band region and we start operating under nominal conditions, we can see that the recovery rate increases exponentially at this point. So relative to the maximum throughput point, and in comparison to the conventional design, the EDS is able to provide a 16% throughput gain. So now I'm going to show the tunable replica circuit, the TRC, and here we can see the maximum throughput point occurs where it provides a 12% throughput gain relative to the conventional design, which is less than what we saw for the EDS, and it's less for 2 reasons. One is that we have to provide some amount of guard band to ensure the TRC is slower than the actual critical path. So that reason we can't exploit path activation. Another important point is that with the TRC, a dynamic variation can occur, but if you're not exercising your critical paths, you may not actually have a timing failure. And so with the EDS, you're only going to recover when you have a real timing failure. With the TRC, all we know is the TRC failed, so we assume there could have been a failure. So a lot of times we're going to initiate a recovery that wasn't required. And so that results in unnecessary recovery. But this is showing the EDS is showing a better benefit. The TRC achieves the majority of the benefit of the EDS, and it's much easier to design. But this is at 1 volt operation. Now, this figure here elucidates a key distinction between the tunable replica circuit and the EDS. And this is plotting the throughput gain versus the supply voltage. And if we go back at 1 volt, the data I just showed you in the previous plot, so we have a 16% benefit for the EDS and a 12% for the TRC. Now, as we go down in voltage at 0.8 and 0.6 volts, what's going to happen is that now the delay sensitivity is much greater to variations in voltage. So the dynamic delay variation is much greater, it's much wider as a percentage. So there's a much larger amount of dynamic delay variability. And we can see that at 0.8 volts, the benefits of the EDS is about 28% and the TRC is at 30. And then when you go at 0.6 volts, we can see that the EDS maintains at 28%. And the reason is because for the EDS, you're going to maximize that error detection window based on Mendeley constraints. But once you're constrained by your Mendeley, you cannot increase that timing window any further, and that caps your maximum potential benefits. So because of the Mendeley constraints, this prevents the EDS from detecting a wider dynamic delay variation, which is occurring as we go to lower voltages. In the case of the TRC, it's not limited by the Mendeley, so it can detect a much wider dynamic delay variation. And as shown here at 0.6 volts, it can achieve approximately a 50% benefit relative to a conventional design. Because again, that error detection window for the TRC is not limited by the core Mendeley constraints. So the key is that the TRC is less intrusive and it provides a much greater ability to detect a wider dynamic delay variation. Now, if we kind of recap at this stage of the presentation, I want to talk about the key feature of the traditional adaptive approach is there's a low overhead. It's not intrusive and it's easy to implement, relative speaking. The key challenge, however, is that the response time limits the benefits. The resilient design relaxes that response time constraint, but there's a tremendous design complexity for implementing error recovery into a high-performance processor. What I just showed in the examples here is recovery, but it was a relatively simple research core. I'm unaware of a recovery that's been implemented in a real high-performance design. I'd point out, I don't think this is a fundamental issue, but it's like a practical challenge in the industry today, and I'm not aware of this actually being implemented for that reason. So that's what leads us to looking at adaptive designs specifically for fast changing variations, and I'm talking about high frequency supply voltage groups. So first I want to talk about an adaptive frequency system, and this was work that was first done at Intel. And the idea that this is a very clever design where this is a core, this is a CPU core, and the voltage that's running the core is also going back to the PLL. And it goes into this mixer circuit where they're going to mix. Typically, you only use like an analog supply to control the VCO. The VCO is a voltage-controlled oscillator. But they're also going to use the digital supply, and they're going to mix that voltage with the analog voltage in order to power the VCO. And the idea is that when a droop happens, then they ideally want the frequency to adjust as well to compensate for the slowdown in the data path. And this is, I think, like from a design perspective, this is a really impressive design. The challenges with this is that these analog complexities really limit the benefits. So the one is from the PLL stability point of view, limits how much of that core voltage could go into the VCO, so limited how much that VCO could change due to changes in the core supply, and that limits the potential benefits. Furthermore, if you go down to lower dynamic voltage frequency scaling, DCVS conditions, there was a short circuit power where you had to completely turn this off. And another concern you had to worry about is that if you have a low frequency droop where the droop goes down and the PLL is at a low value for sustained time, the PLL bandwidth is going to try to quickly increase that frequency. And by doing that, that can lead to a potential timing violation, a timing margin. So really, it's a lot of the analog circuit complexities, but I think there's a lot of insight gained from this design. So now this is leading to the adaptive clock distribution, the ACD. And the idea of the ACD is that it aims to utilize the traditional adaptive approach while specifically addressing the response time. And the way to think about this is that we first want to talk about what happens in just a conventional processor before leading to the ACD. So we have a phase lock loop, a PLL, and it's operating on a separate power supply, a VPLL. And the output is defined as clock root, the root of the clock distribution. And this clock root is now the signal is going to propagate through the clock distribution. Note that the clock distribution is operating on repeaters that are supplied by voltage, VDD, the core voltage. And this is what we have on a conventional processor. And ultimately, it's going to drive the local clock leaf node. So when a droop happens, we have a tendency to think, well, it just hits the data path and we have a timing margin failure. But it also affects the clock distribution path. And so because of that, there is this temporary effect called clock data compensation, such that as the voltage is ramping down, then the delay from the clock root to the clock leaf, which is going through these repeaters, which now the voltage is going down on that, is now going to increase that delay. And because it increases that delay, it's going to stretch the clock at the leaf node. And that stretching can temporarily compensate for the slowdown in the data path. Conversely, if the voltage is ramping up, so now the clock root to clock leaf is actually going to become faster because the voltage is going higher. And because of that, now what's going to happen is that you can actually have a clock compression. The clock can actually shorten when that occurs. But in that case, the data path will also become faster and can temporarily compensate for that clock compression. Now, if you're like me, the first time I was working through this, it took me a while until I went through some basic examples. So I just want to show a simple hypothetical example to understand the concept of this clock data compensation. Clock data compensation. So here in this figure, I'm showing a supply voltage at nominal operating condition. And then I'm just making a very simple, there's a hypothetical just to understand the basic concept. I'm going to assume this voltage is going to immediately drop and just stay at this low value, okay? Now, the clock root is operating at a gigahertz or 1 nanosecond clock period, and because this is operating on a VPLL, it's a quiet supply, it's always going to continue to produce the same clock period regardless of the droop, because it's independent of the actual core voltage root. And then there is the clock root, there is a delay to produce the value of the clock leaf. And I'm going to assume in this example that we have a 1 nanosecond clock distribution under nominal operating conditions between the clock root and the clock leaf. And under nominal conditions, we also have a 1 nanosecond clock period at our data path. And then we have a data path that's switching every cycle in this example. And in this case, we have a 1 nanosecond data path delay. So if you look at the timing margin is the leaf clock period minus the data path delay, which means we have a 0 nanosecond timing margin for cycle 1. Now, on the second cycle, we have this supply voltage droop that occurs, and it occurs immediately. And I'm going to assume in this simple example that the delay is going to change by 25%, okay? So when this happens, now instead of taking 1 nanosecond from going from root to leaf, the delay from root to leaf is going to increase. It's going to increase to 1.25 nanoseconds. But since this clock edge is relative to the previous clock edge based on nominal conditions, the clock has effectively stretched from 1 nanosecond to 1.25 nanoseconds. And now if you look at the data path delay is also going to increase, to 1.25 nanoseconds. So in cycle 2, what you have is that the clock has stretched and compensated for the data path degradation. So this is a clock data compensation effect. And so instead of failing immediately in cycle 2, we actually pass cycle 2, our timing margin is maintained. Now let's look at cycle 3. So in cycle 3, the delay from root to leaf, it's going to remain at 1.25 nanoseconds. But now this delayed edge, instead of being in cycle 2, we had the delayed edge compared to an edge at nominal conditions. For cycle 3, we're going to have a delayed edge compared to a previously delayed edge. So now the clock is going to compress back to 1 nanosecond, okay? And the data path delay is going to also remain at 1.25 nanoseconds. So in this case, there's no clock data compensation and the failure occurs. So what's interesting is because we had that 1 nanosecond clock distribution delay, instead of, if we didn't have the 1 nanosecond clock distribution delay, we would have failed cycle 2. There would have been no clock data compensation. But because we had that 1 nanosecond clock distribution delay, we're able to have the clock data compensation effect, we passed cycle 2 and failed cycle 3. Now what's interesting is if I would have changed this example and I made our clock distribution delay 2 nanoseconds instead of 1, we would pass cycle 2 and cycle 3 and we would fail cycle 4. If I made it 3 nanoseconds for the clock distribution delay, we would pass cycle 2, 3, and 4 and we would fail cycle 5. So this is showing that if the delay that we put in this, it basically prolongs when the timing margin degradation would actually occur in the critical path. So the adaptive clock distribution exploits this clock data compensation effect during the supply voltage droop simply to provide a response time that allows us to detect a droop and adaptively respond. And so to do this, there is this tunable length delay circuit, as shown here. We call this a TLD. And this TLD is going to provide the amount of clock data compensation such that we can detect a droop with a dynamic variation monitor, which we refer to as a DVM. And it's a path-based monitor. It's very similar to the TRC that I showed earlier. And then we're going to interface with an adaptive control circuit and a clock divider. So the TLD, or the amount of time it takes us to detect and adapt to respond, is 2.5 cycles. We've got to detect for 1 cycle, and the synchronization is 1.5 cycles, the way we do that. And then what happens is that we're then going to reduce the frequency at the output of the TLD. Now, a really important point is that you must change the frequency at the output of the TLD. And the way to think about this is that at any point in time, there are clock edges that are going through the TLD and the clock distribution. And when the droop occurs, all those clock edges will clock data compensate, but the new edges that come out of the PLL will not clock data compensate. So you must be able to detect the droop and adapt to respond to prevent those new edges that are coming out after the droop to protect the timing margin in the data path. And so we're going to calibrate that TLD in time to detect the droop and adaptively respond. Now, we had some initial implementations of the ACD, and it was successfully mitigated the impact of droops on performance and energy efficiency across a wide voltage and frequency condition. The big challenge, however, is that the DVM, the dynamic variation monitor, required calibration. And its extensive tester calibrations support a wide range of frequency, voltage, temperature, and process conditions. And so the idea is that this would be prohibitively expensive for high volume products. And that was a major limitation to actually deploy this in a product. And that's what led to the auto-calibrating adaptive clock distribution design, as shown in this figure. So here we have the PLL, and it's generating the clock root. This is then going to propagate through that tunable length delay, the TLD. The output, the clock TLD, will eventually go through, this whole box is the ACD, and eventually it's going to go through to the clock distribution to drive the processor sequentials. So the TLD provides a response time. Then we have a DVM, refer to it as a DVM root. It's a path-based design, and the reason we call it a DVM root is because it's the clock root signal that is driving this. And the key is that because it's a clock root driving a DVM, there is no clock data compensation effect. The data path degrades, and we immediately get a failure. So if a droop occurs, it's going to detect this, and it's going to generate an error signal. This error signal will then be synchronized, and it's synchronized to the negative edge of the TLD, and then it interfaces with an adaptive control unit and clock divider, which is going to reduce the frequency immediately in half to maintain correct operation throughout the droop, and then after the droop's resolved, it's going to come back to the target frequency. The key feature to allow this to really go into a product is this auto-calibration circuit that's going to optimally configure the DVM in field to maximize the ACD benefits. And what happens is that when we calibrate this in the field, so anytime we're going to change a voltage or frequency condition, anytime you boot up or you're coming out of sleep state, anytime you're going to a new operating point, we're first going to put the processor in a safe mode, which means we can operate at a lower frequency, or we can even, while we're doing this calibration, which occurs very quickly, we can even take the frequency all the way down. And what it's going to do is we're going to calibrate this DVM to a 0 timing margin, and then we're going to remove a programmable amount of delay. And we refer to this as a DVM margin, and by removing this programmable amount of delay out, that avoids responding to very small magnitude droops that occur frequently, because we only want to respond to large magnitude droops, which significantly degrade the performance and energy efficiency. Also, there are circuits. There's a frequency counter circuit that allows the TLD calibration, and there's also another DVM that I have in this design. It's called a DVM leaf. It's exact same as a DVM root, except now this is going to be clocked by the leaf clock. So after it's gone through the TLD and the clock distribution, this is where we're going to clock, and we can actually capture this data with a DVM diagnostic logic to provide on-die observability. So here's some measured data that highlights the impact of this tunable length delay. And this graph is plotting the DVM timing margin versus time. And this is showing at a clock frequency of 2.5 gigahertz. So that means your cycle time is 400 picoseconds. The voltage is 0.9 volts. 10% supply voltage Droop is being induced. And since we have a 400 picosecond cycle time, we calibrate the TLD just to demonstrate the effectiveness, how this works. And we calibrate this to 2.4 nanoseconds. That corresponds to 6 cycles of clock data compensation. So the black curve is the DVM root, which again is being clocked by the root clock. So when the voltage degrades, the DVM timing margin, the DVM root is going to immediately degrade. But in the case of the leaf, it has this clock data compensation effect. It's really providing a measure of the actual critical paths. And so what happens in this scenario is that when the root starts to degrade, there's an additional 1, 2, 3, 4, 5, 6 cycles such that the timing margin of the DVM leaf is unaffected. And this shows the ability to postpone when that critical path timing margin degradation occurs. And this provides an opportunity to mitigate that droop. I meant to mention that, of course, this data is showing with the clock divider disabled because we're just trying to show the effectiveness of this TLD to provide the response time. And so now, by using this, for our actual design, we only set the TLD delay 3 cycles. We did it 6 in this case just as a demonstration purpose. An important point is that this clock data compensation dependencies, it's independent of the voltage droop frequency. It only depends on the tunable length delay. So you can have high frequencies, low frequencies, and you still get the clock data compensation effect. Okay, so here's some measured data that's similar to the data that I showed, or similar plot, I should say, to the data in the resilient design I showed earlier. And here's throughput normalized to a conventional design on the top left axis, and the bottom left axis is the number of cycles at half frequency, and the x-axis at clock frequency. So this is operating at a 0.9 volts. It's a 10% supply voltage droop that's induced, and the TLD delay is 1.2 nanoseconds for the adaptive clock distribution. Now, if we first start with a conventional design, this can operate at 2.95 gigahertz at the right edge without any droops present. And then once we induce a droop, we're able to, it degrades the performance to about 56 gigahertz. And that corresponds to a normalized throughput of 1, as shown here. And what we do is we first are going to operate, for the ACD design, we're going to operate at that higher frequency value, the 2.95 gigahertz. We're going to auto-calibrate. But in this example, we're actually starting with a margin of 0. So we have a 0 timing margin. We're not taking anything out. And then we're going to do a sweep of frequency. So here we're sweeping frequency, and the throughput, again, is a product of IPC and effective frequency. So in the resilient design, when you recovered from errors, you actually had a degradation IPC. Here we're not affecting IPC at all. But because we're operating at half frequency at times, especially when we go into this guardband region, then what's going to happen is that the effective frequency can be impacted, because some of the time you're operating at half value. And so what ends up happening is that we're able to continue to increase the clock frequency, which increases throughput, and then eventually the amount of time in which we're operating at half frequency is increasing exponential, so the effective frequency starts to degrade and we reach a maximum point. And if we compare to this maximum value, we're able to achieve a 10% throughput gain relative to a conventional design. Now, if we then take the auto-calibration, but now we're going to remove 1 DVM margin out. We're going to remove that such that we don't respond to the really small droop events, only the large values. Well, then it pushes out how often we remove at half frequency, and it's able to mitigate almost this entire clock frequency guardband region, and then the throughput gain is 13%. So an important point for this auto-calibration is that it needs to work across a wide range of process variations as well as across dynamic voltage frequency scaling. And here I'm going to first show an example of how this is being measured across 109 parts. So in this case, this is showing the test where we have a 3-cycle response time, an auto-calibration of 1, and 109 parts that are shown. And the benefits range from 8 to 20%. But what's interesting about this is that the benefits of the ACD specifically depend on how much the throughput loss was for the conventional design. And so if we looked at this, the range from 8 to 20% specifically depended on how much degradation occurred in conventional design due to that droop. So we can take the same data and we reorganize this and show how much of the throughput that was lost from the conventional design due to that supply voltage droop is recovered by the ACD. And this is showing that for 63% of the parts, the ACD was able to recover 100% of the throughput loss due to the supply voltage droop. And for 100% of the parts, it's able to recover at least 90% of the throughput loss due to the supply voltage droop. This is a plot across the energy per cycle versus throughput. The black curve shows a conventional design. The blue curve is showing the adaptive clock distribution from voltages ranging from 0.9 to 0.6 volts, where the auto-calibration circuit is going to calibrate the DVM across all of these values. And we see at the high performance mode of VDD of 0.9 volts, we're able to get a 13% gain and a 5% energy reduction. And as we go to 0.6 volts, the variation delay sensitivity is much greater. And so this we can get a simultaneous throughput gain of 30% and energy reduction of 13%. And the reason we're getting energy reduction is because it's operating faster, it's able to clock gate and allow the design to, it's using less energy because it's able to clock gate earlier. Okay, so now in taking this from a test chip to an actual product environment, the ACD requires a 2-step production calibration. So first is the performance test, where you have to calibrate that DVM margin that I spoke about via system-level testing across real applications. And the key here is to use the minimum DVM margin with a negligible performance loss. And then once that has been determined across typical workloads, then there's a stability test where you're going to hammer the design with the Fmax or Vmin test to measure the ACD benefits with synthetics code to determine the largest droop possible, and can the ACD prevent this from hurting the performance of the processor. And the focus here, the name of the game, is surviving the worst case droop event. This calibration is done, and then once we go to high volume manufacturing, there's no calibration required, and it's only functional testing. So in the last couple minutes, I'm going to transition to some future adaptive designs. And first I want to talk about, when we look today at our designs, we have 2 separate and independent control loops. There is a voltage regulation that is striving to achieve a target reference voltage, so a VREF as shown in this figure. And this can be done through a buck regulator, it can be done through a switch cap design or an LDO. And this is trying to maintain a constant voltage to the processor. And then there's an independent control loop that, such as like a phase lock loop, which is constantly trying to maintain a constant frequency relative to a reference clock frequency. And there's a lot of work that's looking at new ways of combining this. And so some of this work actually comes directly from the University of Washington. In fact, these figures come from the author, I think, Shun and Fahim. I think it's coming from their papers here that I'm referencing. So the key is that today's processors generate these voltage and frequencies in 2 separate control loops, and because of that, it's unaware of a voltage change. And so for that reason, we are either going to have to build in guardbands, like in a conventional design, or we have to use adaptive resilient circuits to mitigate those dynamic variation events. So an approach here is looking at unifying this regulation into a single control loop. Or the work at the University of Washington here is a unicap design, unifying the clock and power regulation. And the idea is that this TRO, it's a tunable replica oscillator. Kind of think of it as like that TRC I showed, but instead of using any flops, it's just going to oscillate. And you're going to calibrate this to provide the clock to the processor. And the key is that the processor and this TRO is supplied by the same voltage. And in this case, what happens is that when a dynamic variation occurs, the droop is going to affect the TRO immediately, and it's going to affect the clock frequency. And that is going to provide sufficient timing margin to protect the data path in the actual processor. Now, of course, we have to regulate the clock because we need to maintain a certain clock frequency. So this clock is going to be fed back to another loop. It's going to be compared to a reference frequency. And if a droop occurred, it would either interface with a buck, a switch cap, or LDO to bump that voltage up. So the key point is that if you kind of compare, like in the case of the ACD, I talked about we use temporary clock data compensation to provide the response time to adaptively mitigate the droop. This design provides an infinite amount of clock data compensation. And I think that is a very exciting opportunity. So just to quickly show a demonstration of this, here's an example where there is a voltage droop that occurs. And if the frequency is maintained at 200 megahertz, like a conventional design, we would have pipeline errors would occur. And then if we look at unifying this into a single control loop, when the droop occurs, then the clock frequency is going to intrinsically stretch to maintain the timing margin, and this would avoid the pipeline error signal. So the key is that it's intrinsically adapting to voltage and frequency to avoid timing margin violations. So in summary, adaptive resilient circuits mitigate the impact of these dynamic variation guard bands for higher performance, energy efficiency, and yield. The traditional adaptive approach, the key benefit is that it provides a low overhead. It's a very low intrusive design. It does not impact the actual circuits. And so that is a tremendous feature. And so the challenge, though, with the traditional adaptive design is the response time limits the benefits. For resilient design, it relaxes that response time constraint. However, there's tremendous design complexity for enabling error recovery. The auto-calibrating adaptive clock distribution design aims to retain the low overhead of the traditional approach while addressing specifically the response time problem. And this allows it to have low overhead and be able to mitigate the droops. And by having the auto-calibration circuit, it also avoids the calibration at test time. And I think looking forward, there's an opportunity of combining the voltage and frequency regulation into a single control loop. And by doing this, it's able to intrinsically adapt with an infinite clock data compensation effect. So I thank you for your attention, and I would welcome your questions.
Questions, please, for the speaker? Yeah, one.
So you mentioned one limitation for the adaptive design is the response time, right? And one reason for the voltage drop is since the workloads change. So my question is, if in some cases we can predict the workload, like if you are like a large for loop or something, you know there's a lot of computation or a lot of memory access is coming. Is it possible to design things like a voltage droop predictor or workload predictor, similar like a bread predictor, right? Mm-hmm. Is that possible?
So that's, first of all, that's a great question. So I just want to kind of repeat your question. So the question was, hey, everything I'm showing, it's a reactive design, right? Like it's detecting the effect, and then it's trying to adapt to mitigate what's happening. And so your question is like, well, hey, can you actually predict this ahead of time? Like a priori, can you say, this is going to happen, I know it's going to happen, and do something about it before it happens, right? And so the answer to that, at least from my understanding, is it really, practically, it kind of depends on the type of processor. So I'll give an example. In a CPU, there was research done, and I think there was really interesting work by David Brooks's group at Harvard University. And they looked at this, or at least that's one group I know that looked into this. And what's interesting is that I think a CPU is very hard to predict because there's so many events that can happen. And the other thing is, like, sometimes you can predict, like, for example, a miss branch predict or something like that, and sometimes that can lead to a droop and sometimes it doesn't. So if you start doing the mitigation and it never would have happened, it can really hurt performance. So I think in a CPU, it's very hard. But with that said, I think there are some designs or some processors which I think the opportunity to predict that lends itself better. And so, for example, I know I've talked with some people that work with DSPs, digital signal processors, and there the workloads are much more easier to track. I would also kind of argue, I think, like with machine learning, you kind of know when you're really going to ramp up, when you're going to execute a lot, and when you're going to kind of ramp down. So I do think there are opportunities for certain types of processors, but I think for like general purpose processor, like a CPU, that's very difficult. But I think for certain, like maybe accelerators or ASICs, I think there is an opportunity for that. So that's a great question. So thank you for that.
Any others? Chris?
So it was a very interesting talk. I haven't really looked at this area it's been a long time. So basically when I was in graduate school. So one of the things that I assumed it just wasn't enough time to talk about it, but in these sort of modern methods that people are using to really efficiently run the processor, what about stability of these types of systems, right? Can you run into stability problems? You know, I see VCOs in there, and you know, between like the regulator and the VCO, or you know, something like this. Do you have concerns of that in these types of systems?
So you obviously have, I mean, you're right. You do need to maintain stability through all of this. So what I would say is, I think one of the things that's important to note is a lot of times what I would say is like when I've presented some of this to people like who've been in the industry for a long time, and at first glance, for someone who's really experienced, I think it's as hard to digest at first. And the reason I say that is because we have a tendency to just focus on a data path and separately focus on the clock path. Okay, but really, it's both that matter a lot. So when we talk about stability, what does that really mean? So like, for example, I'm kind of leading into a question, like one of the ones I get a lot is say, well, hey, if I put any delay into the clock path, I'm increasing jitter, right? I mean, that's like something you could argue, does that affect your stability, right? But I would argue that the majority, the dominant component, so jitter is how the clock is going to vary. And the answer is absolutely, that's really what the clock data compensation is about. But the point is that jitter effect is highly correlated to voltage variations. And the voltage variations are correlated to how the data path is varying. So at the end of the day, we really care about timing margin, which cares about the clock path and the data path. If I only analyze the clock path only, then I could really be concerned about, oh, I'm introducing a lot of fluctuation here. But it's a combination of the two. And so, like, for example, like that's something that's really hard to work with a lot of our simulation tools because we don't do it that way, right? It's done in isolation. So that's one of the common topics when I work with a lot of product design teams. I'm just mentioning that as one example and thinking about stability. So stability is definitely critical, and I would kind of argue that a lot of these things even kind of allow us to be even more stable. And so in addition to I didn't get to it here, but in addition to doing variations, there's also, hey, what about like certain limit conditions? Like we can have excess of current, and we have a certain power envelope we have to hit, so we have to throttle back to maintain, that's going to affect stability because you can have like a thermal runaway effect, and so we'd be able to detect that and limit that from happening. So there's a lot of things of how adaptive circuits can be used to maintain stability.
And what's the criteria between stable and unstable? Is it just unstable, you just start making more errors? It's as simple as that?
I would argue from getting back to the timing margin discussion, then yes, it's like, are you failing timing margin or not? That's correct. Right. Thank you for your question.
Good question. Any others? All right, with that, let's thank the speaker again.
Thank you.